Hi everyone. So in today's lecture, we're going to talk about another way to think about determinants, which can be given in terms of the tensor algebra. So to start with, we need to define tensor products. So let M and N be two R modules. Here R is a ring. We will construct an R module M tensor N called the tensor product and the tensor product has the important special property that we have a one-to-one correspondence between sets of multilinear maps and R-module homomorphisms from the tensor product. So the tensor product has the property that we have a natural one-to-one correspondence or bijection between the sets so the set of multilinear maps from direct sum of m plus n to some module p and this set is in bijection with R module homomorphisms from the tensor product to the module P. So multilinear maps from M plus N to some module P are in one-to-one correspondence with homomorphisms from the tensor product to P. Okay, so here's the theorem telling us that tensor products actually exist. So let M, N be R modules, then there exists an R module M tensor N and a multilinear map G from M plus N to M tensor N with the following property. And we call this following property the universal property of the tensor product. So for any R module P, and any multilinear map F from M plus N to P, there exists a unique morphism F prime from the tensor product to P such that f prime, such that f factors through f prime. So the same thing, such that f equals f prime composed with g, where g is the multilinear map that we have from the direct sum to the tensor product. So we call this the universal property star. Okay, so the content of this theorem is that the tensor product, which comes equipped with a multilinear map from the direct sum to the tensor product G, has the property that any R module P together with a multilinear map from M plus N to P factors through a unique morphism from the tensor product to the module P. Okay. So proof. So we consider first the free R module generated by M plus N. So consider the free R module R to the M plus N, which so it's the free R module on the abelian group M plus N, i.e. R to the M plus N is defined as the set of all formal expressions R1, M1, N1 plus R2, M2, N2 up to RL, ML, NL. So all finite linear combinations of elements in M plus N. And these are formal expressions. So here L is positive, M, I, N, I are in M plus N for I between 1 and L. And Ri are in R. So we look at the set of all formal expressions of linear combinations of elements in M plus N. And this is naturally an R module. With S times some linear combination. Being defined as, well, the linear combination with the coefficients multiplied through by S. Okay. So now, let H in R to the M plus N be the submodule generated by elements of the form M1 plus M2N minus M1N minus M2N, as well as elements of the form M1, N1 plus N2 minus M1, N1 minus M1, N2, plus we have the relation Rm1 n1 minus Rm1 n1 and m1 r1 n1 minus, sorry, let's just call this r, minus r m n. So we let H be the submodule generated by elements of the following form. Okay. Then we can take the quotient and we set the tensor product to be the quotient of r to the n plus n on H. Okay, so to understand why we make this definition, if m is in m and n is in n, write m tensor n for the equivalence class of mn in m tensor Rn, which is r to the n plus n of H. And now from the definition of H, so if I call star the set of generators of H, then we see that we have m1 plus m2 tensor n equals m1 tensor n plus m2 tensor n. We have m1 tensor n1 plus n2 equals m1 tensor n1 plus m1 tensor n2. We have rm1 tensor n1 equals r times m1 tensor n1. And lastly, we have m1 tensor rn1 equals r times m1 tensor n1. Here should be m1 n1. Okay, and this holds for all m1 m2 in m, n1 n2 in n, r in r. Okay, so these relations you can check. The fact that we have these relations means that we can define means that well, we have all the kind of natural operations that you would like a tensor product to have. So you have, for your multiplication, you have these natural additions in the first and second coordinate, and multiplication by scalars operates in the natural way with respect to the module structures of m, n, and the tensor product. Okay. So now we can define a multilinear map G from m plus n to the tensor product by G of m plus n. So G of mn is defined to be m tensor n, where m tensor n is the equivalence class of mn as above. Okay, so notice that m tensor n is generated by elements of the form m tensor n for little m in m and little n in n. Okay, so we now need to check that the tensor product as defined has the required properties. So we need to define for any map, for any multilinear map from m plus n, we need to define a corresponding map from the tensor product. So suppose f m plus n to p is a multilinear map. Then we define f prime from m tensor n to p as just f prime m tensor n equals f of mn. And you should check that this is well defined. It doesn't depend on the equivalence class. So m tensor n is it's an equivalence class of representative mn, and you need to check that this doesn't depend on the choice of representative. But that's easy. It follows from multilinearity. Okay, then we have the required properties. Also, I should say that this formula is enough to define f prime. It's enough to know how the homomorphism acts on generators, and m tensor n generate the tensor product. Okay, so we have that f prime composed with g equals f, and further, for any h from m tensor n to p with h composed with g equals f, then h of g mn equals f of mn, but this thing is m tensor n. So this tells us that h of m tensor n equals f of mn, which means if we compare it with the rule for f prime, this implies that h equals f prime. So for any map which factors f through the tensor product, we have to have the h equals f prime, which gives us the uniqueness part of the universal property. So this proves that the tensor product has the required universal property. Okay, so here's a corollary. Let m and n be R modules. Then the tensor product is the unique R module with the universal property up to isomorphism. So the tensor product is the only R module with the universal property up to isomorphism. i.e., if we have an R module T and a multilinear map G hat from m plus n to T with the property star, so with the universal property star, then there is an isomorphism. Whoops. H from T to to M tensor N, giving commutativity of the diagram M plus N goes to T like this. So here G is the natural morphism we defined from the previous proposition from the direct sum to the tensor product. Okay, let's prove it. So, so commutativity is the same as saying that G is H composed with G hat. Okay, let's prove this claim that the tensor product is the only module defined by the universal property as above. Okay, so by the universal property, which we assume holds both for T and for the tensor product, so by the universal property now applied to T first of all, so if we apply this universal property for T to the map G, then the universal property applied to T tells us that the map G has to factor through T. So it tells us that there exists some H from T to the tensor product, giving the commutative diagram that we want. By the universal property applied to T, which we're assuming satisfies the universal property. Okay, so what we need to show is that H is actually an isomorphism. But we also know that the universal property holds for the tensor product, so we can use that here. So we now replace T and the tensor product in the argument. So by the universal property for the tensor product, there exists some J from M tensor Rn to T such that we have a diagram, a commutative diagram like this. Here we have J, here we have G hat, and here we have G. Okay, so we need to prove that G and H are inverses. Okay, so if I put these two commutative triangles together, we have commutativity of M plus N, M tensor Rn, M tensor Rn, G, H composed with J. Okay, but of course, since two of these sides of a triangle are just the same map G, one also fits into this diagram. Okay, but the uniqueness part of the property star tells us that 1 is the only map which can fit into this diagram. So then we must have that H composed with J is the same as 1. And by the exact same argument, we can get that, if we go the other way around, we also get 1. Okay, so this completes the proof. And now to end today's lecture, I'd like to talk about some properties of the tensor product. So let M, N, and P be R modules. Then we have isomorphisms. One, from the tensor product M tensor N to N tensor M, other way around, so we can swap the order of the terms in the tensor product. 2, M tensor N tensor P is isomorphic to M tensor N tensor P. 3, M plus N tensor P is isomorphic to M tensor P plus N tensor P. And lastly, R tensor M is just isomorphic to M itself. And these isomorphisms are given by, so the first one is given by M tensor N goes to N tensor M. The second one is given by M tensor N tensor P goes to M tensor N tensor P. The third one is given by Mn tensor P is mapped to M tensor P N tensor P. And the last one is given by R tensor M is mapped to Rm. Okay, so to prove these properties, you want to use the universal property again. So these are all proved. Using the universal property in a very similar way to the corollary above. So let me just do one of them for you, and then I will let you do the others. They're all very simple. They're all very similar. So for example, for 1, the composition of multilinear maps. So we consider the following composition of multilinear maps. We have M plus N goes to N plus M by swapping the orders. So M, N goes to nm, and then this goes to n tensor m. And this gives us a map from the direct sum of m and n to the tensor product of n times m. But now, by the universal property, this induces this composition from m plus n to n times m induces a morphism m times n to n times m. And likewise, and this is given by the map m times n, little m times little n gets mapped to n times m. Likewise, now doing the exact same argument, but with the order of m and n reversed, then we have a natural morphism n times m to m times n, just by repeating the argument, but with the order of m and n reversed. And then, exactly as in the corollary, the uniqueness part of universal property implies that these two morphisms are inverse. So as in the corollary, the uniqueness in the universal property implies these morphisms are inverse. Okay, so the other parts are similar, and I'm going to leave them as an exercise. Okay, so let's just end today's lecture with a very simple theorem, which is also proven once again using the universal property. So if you find today's lecture a little bit confusing on the universal property, then I recommend that you read the section on tensor product from the textbook and try the exercises. There are lots of exercises there which can be approached using the universal property. Okay, so let f from m to n prime and g from n to n prime be two R-module homomorphisms. Then we have the following theorem. And this theorem tells us that we can take the tensor product of homomorphisms. Okay, so theorem, there is a unique R-module homomorphism f tensor g from m times n to n prime times n prime with the property that f times g of m times n equals fm times gn. So if I have two module homomorphisms, then I can take the tensor product of the homomorphisms to get a homomorphism between the tensor products. Proof. So consider the bilinear map f times g from m plus n to n prime tensor n prime, defined as f times g of mn equals f of m tensor g of n. Now the universal property for the tensor product shows that f times g factors through isomorphism with f times g acting on the tensor equals to fm tensor gn, which was the formula we wanted. So this just follows immediately from the universal property. And then, well, since the elements little m tensor little n in the tensor product of m and n generate the entire module, there can only possibly be one module homomorphism with this, given by this formula. Okay, so that's the end of today's lecture. I know this was a little bit abstract, but after you do a few exercises on tensor products, you should get pretty familiar with it pretty fast. And then we're going to use this to develop some more theory and talk about things such as the